All right, so let's talk about one of the more complicated aspects of these reactions, and that's the stereochemistry between these alkenes and these addition reactions. So notice that I'm talking about stereochemistry, not regiochemistry. Right, regiochemistry would be something like Markovnikov versus anti-Markovnikov. Right, so we're not talking about which one's going to go on the more substituted, the less substituted. We're talking about the stereochemistry of our products. Are we going to get one enantiomer, two of the enantiomers? What are we going to get, right? And so this becomes complicated when you have these alkenes with 4 different substitutions, right? Because when we add across this alkene AB, what we form is something like this, right? And what you notice here about these compounds is that there's 2 stereocenters. And so if there's 2 stereocenters, there can be up to 4 products. Remember, we said 2 to the number of stereocenters. That's how many stereoisomers there can be. So there can be up to 4 different stereoisomers, right? And them being RR, SS, RS, and SR, right? And so there's a bunch of different reactions that we learned. Some have importance in these types of alkenes, some don't. And so these ones, the first list I'm going to give you are not important. Basically because they're going to give all these stereochemistry products. Right, they'll give all 4 of them, and so you can just draw with no stereochemistry involved because you have an even mixture of all of them, right? And that's any reaction that has the addition of HX, HBr/ROR, the peroxide. When we add acid across a double bond, right, our acid catalyzed hydrogenation. And then finally, our oxymercuration, demercuration reaction. And the reason for this is that they all go through some kind of carbocation or some kind of radical mechanism. At least in some part. And so what that does, it just scrambles all the stereochemistry. And so what you end up with is a mixture of all 4 stereochemical possibilities. And then we moved on to some other types of reactions, and these other types of reactions can either add syn or they can add anti to one another. And so in this case, it will matter. So first for our syn, we had our BH3 and THF, right, borohydration, followed by our oxidation. And remember, this adds a hydrogen and an OH syn with one another in an anti-Markovnikov fashion, if you want to think about the regiochemistry. We had the H2 with a catalyst, our hydrogenation. This adds H and H syn with one another. And then we had our syn dihydroxylation, right? Adding 2 OHs with our osmium tetraoxide and NMO. Or you could use the permanganate base in cold conditions. And then for anti, we had the addition of X2, where X is chlorine or bromine, right? That's going to add X and X across the double bond in an anti fashion. We had X2 and then water, right? That's going to add X and OH across this double bond, where this OH gets the more substituted position. Because remember, it's going to go through that brominium or chlorinium ion. And then we had MCPBA that'll form the epoxide, followed by adding some kind of nucleophile H and some acid, right? And that'll add a hydroxide and an NU, right? Usually another OH is usually add 2 alcohols, right? So it's the anti-dihydroxylation, kind of the opposite of this syn dihydroxylation. And so that's one thing that we have to consider is whether they're going to add syn or anti. The other thing we have to consider are our substrates. slash the products when we're thinking about the stereochemical outcomes. And so if we have something that is symmetric alkene, right, when we add across A and B, if we think about when we add A and B, it doesn't matter what A and B are, there's no stereocenters here. And so you only get one product because there is only one product, right? There's no enantiomers, there's no stereoisomers for this compound. And so it doesn't really matter there. Another option would be something like this alkene, where when we form our product, we do have a stereocenter, right? So we could put a B as a wedge, or we could put a B as a dash. And so here we only have one stereocenter. And whenever this happens, we get a racemic mixture. And so this has to do with our addition components, either adding from the top or the bottom. There's not going to be any preference for it to go from the top or the bottom. And so you're going to get a racemic mixture. And so again, the stereochemistry here doesn't really matter. We could draw this product like this, and it's still a correct answer, right? Indicating a racemic mixture. Where it gets complicated is something like this. Here, where we add A and B across here, we now install two stereocenters into our complex, right? Assuming B is not a hydrogen. And so whenever we have two stereocenters, we're going to have up to 4 products, right? Maybe not 4 products, but up to 4 products, right? Because we have 2 to the squared, 2 to the 2 is equal to 4, right? And so we have to think about the ways we can add them. And as we discussed previously, there's 2 main additions, right? We can have syn addition, or we can have anti-addition. And so let's take a look at that and the stereochemical outcomes of that. Just going to redraw this double bond, right? And so one option is for the syn addition. So like look at syn first. And so the syn, if they're adding syn, both of the components can either add from the top of the alkene or from the bottom of the alkene. And so if we're thinking about adding them from the top, right, what are they going to be? Well, they're both going to be wedges, right? Wedge means coming up top, right? And then if they're coming on top, something has to get pushed back, right? And in this case, it's going to be this methyl because of the way I drew it. That's going to get pushed back into the board. Right, so that's one option for it to occur. The other option is to have them add from the bottom. And so if they add from the bottom, they're both going to be dashes. And then if you think about what's going to happen to this metal, it's going to get pushed up and out of the board. And so once we add these things across, we'll get this. But either way, in either product, you see that we've added them syn to one another, right? And so that's this whole set of reactions right here. And then when we add them anti to one another. Notice though that we didn't touch this stereocenter at all, right? We're not reacting with that stereocenter, so it's just gonna chill out there. And so here they're adding anti. So one option is A comes from the top, B comes from the bottom. And so if A is coming from the top, it's going to be a wedge. If B is coming from the bottom, it's going to be a dash. And then A is going to push this one down, right? Push this methyl down. right? And we end up with that stereoisomer. The other option is for A to come on the bottom and B come from the top. So if A is coming from the bottom, it's going to be a dash. If B is coming from the top, it's going to be a wedge. And then if we're thinking about what's going to happen to this methyl, it's going to be pushed up. And it's going to become a wedge. And so you can see in both of these outcomes, A and B have been added anti to one another, right? And so that's how you can imagine it. It's pretty easy with cyclic compounds. You can imagine both A and B coming from the top or the bottom. It gets a little bit more confusing to look at when you think about non-cyclic compounds. So something like this. Right, when we add A and B across here, we end up again with 2 stereocenters, and so up to 4 products, right? 4 stereoisomers, right? And so the question is, which one will you get and how do you predict this? So there's multiple ways of doing this. I looked online for various methods. I was kind of a little disappointed with kind of what was out there. So here's kind of the one that I think is the easiest to do. This isn't quite the way I think about it, but I think it's easier. And so basically what you want to kind of do is look at in the plane of the alkene. So here's just some Google images I found. That can give you some kind of keys, right? And so especially in this picture right here, right, you see this alkene here. What they're thinking about is look at it as though it's perfectly flat, right? We're looking where these two are in this, where all 4 of these or all 6 of these components are in the same plane. And then we're going to add stuff, either syn or anti to one another, right? In this case, we're going to add anti. So one Br will go there, one Br will go there. And you can see how where we're wedged here, we're still kind of wedged over here. They messed up some of this drawing though, so it's not that great. So I'll go ahead and show you. And you can look at the same thing here, what they did here, right? You see these R's, you see they become kind of wedges or dashes in these intermediate pictures. And so let's go ahead and redraw our substrate. And then we're going to think about this being flat. And so we see that these two are kind of cis with one another. And so they're kind of, I'm going to just arbitrarily put them in the back of the board. You can put them in the front of the board too. It doesn't matter. They just have to be on the same side, right? And then these two are cis with one another. And so we're going to draw these both as wedges. And then we're going to try to look at some mechanisms, right? Or some intermediate type of things, right? And so we can add syn, where both of them come from the top, right? And so if you think about adding A and B right here, right? We added A and B there, and then we keep everything else the same, right? This methyl is wedge, so we're going to keep it wedge. This ethyl is dash, we're going to keep it dash, but everything's going to get pushed down, right? This tert-butyl is wedge. Extra thing there. Tert-butyl is wedge, and then this isopropyl is dashed, right? And so you can see we've added both A and B from the top, and you can see the stereochemical outcome here. And so this drawing is totally okay if you want to leave it like that. The only kind of issue really is it's eclipsed, which isn't a big deal, but it's obviously not the best conformer it could be in. So if you'd like to make it look a little bit nicer, it's optional to rotate this molecule to have it what it really look like, right? So we can rotate about one of these bonds and just put them in a staggered conformer. So I'm just going to keep A where it's at. And then I'm just going to rotate B a little bit. So that way we're nice and staggered. And then you can think about where all the other stereochemical outcomes will be, right? But if you want to just leave it here, that's totally fine. The other option would be to add it from the syn from the bottom, right? And so in this case, we're adding A and B from the bottom. And if this is totally flat, right, the wedges and the dashes are going to stay the same. They're just going to be pushed up a little bit. Right, just pushed up a little bit. And again, we can rotate about this if you don't want to leave it in this eclipsed conformer. Leave this A where it's at. And then we'll just stagger B. And then reproduce all the stereochemical outcomes. But if you want to leave it in this position, that's totally fine. And so you can see how if you view this alkene as being planar, then you can see how these additions from the top or the bottom of the syn addition is going to give you what products you want to get. And then, of course, we could do anti-addition. Right, and so there's obviously different things we could do. We could add A from the top side, right? So we're adding A from the top and then B from the bottom side. And think about what that's going to look like, right? We'll keep A and B in the same plane, and our wedges will continue to stay wedges, and our dashes will continue to stay dashes. They're just going to get pushed up or down a little bit. So that'll still stay totally like that. And then the other one obviously is to go anti and B from the bottom. Oops. A from the bottom. So instead of putting A on the top there, we're going to put A on the bottom here. And think about the stereochemical outcomes, right? A, B. And then we're going to keep our wedges, wedges, and keep our dashes, dashes. And you see with these anti-addition, we're already in a clip or a staggered conformer. And so we're totally okay. So this is definitely one of the more advanced kind of ideas with the stereochemistry of these very asymmetric alkenes and how you add them across a double bond and which of the four or which of the two enantiomers do you get, right? You always get a set of two unless your compound can be meso, right? So watch out for meso compounds. Remember, a meso compound is a compound that has two stereocenters, but there's a plane of symmetry. And so two enantiomers, or two things that look like enantiomers, actually aren't enantiomers. They're the same product. So we can think about this trans alkene and adding X2 across this trans alkene. And so we can think about this trans alkene as being totally planar, right? This is going to be a wedge methyl. This will be a dash methyl. And then we can add in the hydrogens just so we see them nicely. And then what we're going to do here is add some stuff anti to another. So we could add X up top and X down here. Or we could have it the other way, right? X first adds down here, and then X adds down there. And then you keep the wedges, and the dashes, right? So there's a wedge methyl here, wedge or dash methyl there, wedge methyl here, dash methyl here. And so if you think about rotating about this bond, keep this one the same, and then just rotate this other side so this X is also facing down. If this X is also facing down, this is then going to go into a wedge. and there'll be a mirror plane there, right? And so these two are actually the same compound. You notice that in order to get these meso compounds, we have to have added something that's the same, right? If you add an H and an OH, they're not really going to be meso. You have to add the same thing across both double bonds. Whereas if we had the cis version of this compound and we added X2 across this, again, we can think about this alkene as being totally flat. So I'll just draw my methyls as dashes and then the hydrogens as wedges. And then we can think about adding this first X on top and the second X on bottom, or vice versa. And then keep all the methyls the same, right? They're all still just wedges, or dashes, my bad, dashes. And so that would look something like that. And then if we try to rotate about this plane of symmetry, we'll leave this one the same. The methyl goes there. If you think about putting this X down here, it's actually going to be a wedge. And so there's no plane of symmetry. And so you actually get two products, or two of the stereoisomers. And so just review, right? This is the stereochemistry. This is definitely a more advanced topic. So if you're struggling with other stuff, focus more on that other stuff. This is just kind of an ancillary, more advanced kind of thing to think about if you're on that level, right? We have things where the stereochemistry doesn't really matter because we get all of the stereocenters. And then we have syn and anti-addition where the stereochemistry does matter how we add it. And then we have to think about the substrates that we're adding. If our substrate has no stereocenters in the product, we don't have to worry about it. If it has one stereocenter, we're going to get a racemic product, so we don't have to worry about it. And then if it has two stereocenters, that's where it gets complicated. But again, it's more of an advanced topic. So if you're not too comfortable with this, don't spend too much time on it. Spend more time on learning kind of the mechanisms and the regiochemistry of them.